Wolfgang, sorry that we make you wait a bit.
No, that's all right. With international time zones and everything, that's all good. No worries.
Yeah. I think they're coming already. I see some of them. The timer is coming from here.
Hey guys.
So it's not streaming?
I guess you need us to speak on the microphone, right?
Yeah.
That I could hear before, but this sounds a lot clearer. Thank you.
Right. So I'm going to pass the microphone to the president of the jury, Maud Marshall.
Maud.
Okay, so good afternoon and good morning for Wolfgang. so it's my pleasure to introduce the committee for the defense today of Aziz Niyazov. So the jury will be composed of two reviewers. So Professor Wolfgang Sturzinger, professor at Simon Fraser University in Canada, and Gilles Bailly, director de recherche CNRS. And then the jury is also composed of the two supervisors of the PhD student. So we have Professor Loïc Barthes and Dr. Marco Serrano. And myself, I will be the president. I am professor in Rennes. So Aziz, you have like 45 minutes to present your work, and then we will have questions.
Okay. Well, thank you very much for the introduction. So I guess I can start, right? Okay. So I would like to present you my PhD work on pervasive freeform user interfaces. This work lies within the HCI research field and applies computer graphics methods for the interfaces that can be displayed anywhere. This PhD is the result of collaborative effort of Ellipse and Storm research groups at ERIT Lab in University of Toulouse 3 in France, as well as data visualization and immersive analytics lab in Monash University in Australia. In this presentation, I'll first start with the introduction of ubiquitous computing and its challenges. Then I'll give you some insights of the related works. After, I'll present you two of my works. The first one is the dynamic decals, and the second one is the user-driven constraints. Last, I'll talk about the research direction following my PhD research. Starting with the UbiCom, or ubiquitous computing. Ubiquitous computing is the notion that corresponds to access of information anywhere and anytime. The evolution of ubiquitous computing started with the mainframe era, characterized by one powerful central computing unit serving for many users. Later, the introduction of graphical user interfaces changed the way how people interact with the machines. The personal computer era brought the computational power directly into people's homes and offices, as these interfaces became more intuitive and easy to use. With the further advancement in technology, portable devices such as smartphones became widely available for public. Today, we are in ubiquity era. In recent years, the concept of ubiquitous or pervasive interfaces gained the popularity driven by the need for the consistent and interactive experience across the devices. These interfaces have a broad application starting from smart buildings to education, entertainment, healthcare, and entertainment, transforming interaction and data visualization for the diverse users. Pervasive freeform interfaces are not limited to traditional rectangular. Pervasive interfaces are not limited to traditional rectangular display areas. Such non-rectangular or freeform interfaces take their roots in organic user interfaces and shape-changing interfaces. They can be defined by three main principles. The first principle is the input equals output. Means that the display should follow the shape of the object and the input method should correspond to the such display shape. The second principle is function equals form, states that the form of the object should determine its function. The third principle is form follows flow, express interface adaptation to follow the user activities and better fit a particular context fluidly. Nowadays, we are already familiar with some of the commercial forms of pervasive freeform interfaces. For example, smartphones having rectangular with rounded corner screen, circular smartwatches, and the freeform car dashboards. The pervasive freeform interfaces can be also presented in immersive environments, such as augmented reality and virtual reality. My PhD focused on creating the interaction paradigm for the user interfaces not presented in the rectangular display shapes. We are interested mostly in two forms of pervasive interfaces, 2D projected and immersive augmented reality interfaces. These interfaces are characterized by the freeform display area, dynamic content, spatial interaction, and complex layout. However, these interfaces bring new challenges. The first challenge is the interface adaptation to a freeform display area, which leads us to the first research question of how to adapt the interface to the freeform display area and the presence of the physical objects that can occlude the interface. The second challenge is the dynamic change of the display area. In such pervasive context, the interface should be adapted dynamically to the available display space. This poses an additional question for the outer shape or inner holes. For example, when a user moves a cup over the interface. This leads us to the second research question of how to dynamically adapt the interface due to the presence of the physical objects. The third challenge is the lack of user control over the optimization. Allowing users to control content organization is very critical and efficient for data access. However, manually arranging virtual content in the surrounding real world is very tedious. In contrast, automatically optimizing the content placement removes any need of the user input, but lacks the user control of the resulting placement optimization. Therefore, there is a need of human in the loop, which raises the question of how to bring the interactivity into layout optimization systems. The third challenge is the spatial interaction to control the interface layout. Immersive environments require different modalities for spatial interaction. For instance, augmented reality headset displays and enable users to organize virtual content using hand gestures. However, such technologies rely on the legacy of the graphical user interfaces, such as menus or UI widgets. Hence, there is a need for the holistic and intuitive interaction that allows any user to guide the layout optimization in the real world quickly. Which brings us to the last research question of how to provide a set of spatial gestures to control the layout optimization while not depending on the graphical user interfaces. After defining the research questions, we address them separately in two of our works, dynamic decals and the user-driven constraints. Dynamic decals serves as the foundational step in our research, simplifying the problem and laying the groundwork for the further exploration. The user-driven constraints focus on the immersive aspects, gradually progressing from simpler to more complex concepts. Before diving into our contributions, I will first present the approaches of the previous works. We categorize them in 3 groups. The first group describes how layout is organized in static interfaces. The second group explains how the virtual content can be adapted in dynamic context. And the last group presents the layout optimization techniques. We reviewed the related works for flat and freeform, for flat rectangular and freeform interfaces, as well as their placement in the immersive environments. Previous works have demonstrated that the layout organization on rectangular and freeform layouts relies on Gestalt laws. These laws are applicable to enhance the visual composition and the aesthetics of the interface. In the immersive environments, virtual content can be fixed in the environment or movable. Also, it can be presented with the egocentric or exocentric perspective. However, these works were not focusing on the dynamic adaptation of the content when transforming content from rectangular display areas to the freeform ones. To address the dynamic challenges, previous work presented the approaches to handle the occlusions by repositioning the occluded content into the other area of the interface. Also, the graphical user interface layouts adapts to non-rectangular displays by content mapping or content deformation. To facilitate the interaction for the immersive layouts, previous work have explored the effect of the layout curvature and allowed body-centric interface adaptation. However, the main limitation of these approaches is that they are not space efficient because they do not maximize space occupation. They are just rearranging the rectangular windows on the available display space. Also, in the previous work, the whole windows is warped, which impacts the visibility of the content, particularly the UI elements that are very close to the edge of the windows. Layout adaptation in the immersive environments raises the challenges of the spatial content positioning, especially when there is a large number of virtual objects. Layout optimization is essential in pervasive dynamic context, as it allows users to arrange virtual content without the need for tedious and manual interaction. Previous work have proposed an optimization approach to generate layouts using constraint-based approaches. However, these approaches didn't address the challenges of layout optimization in the freeform interfaces. In the immersive environments, previous work introduced the multiple constraint-based approaches to optimize content placement and removing any need for the user input. This optimization approach explored the use of geometry of the environment, spatial consistency, user perspective, usage frequency, or semantics. The limitation of this optimization approach in rectangular layouts that they mostly rely on the flow and grid layouts. In the immersive environments, the previous works are limited in 2 aspects. First, for the most part, these constraints have been tested in isolation from each other, leaving aside the question of how to allow the users to define several constraints in a fluid and natural way. Second, most of these approaches lack any form of the user control over the resulting placement optimization. We thus lack a holistic approach that unifies multiple constraints and input interaction, which bring interactivity into augmented reality layout optimization. We group the limitation of previous works and address them in our 2 complementary works. In dynamic decals, we proposed the layout optimization model, adapting graphical user elements depending on the user interaction and constraints. In the user-driven constraints, we bring interactivity into layout optimization systems. To this point, I presented you the challenges of the pervasive freeform interfaces and how the previous works try to address them. Now let me start with our first work, dynamic decals. In this work, we adapted the interface to freeform display areas and the presence of the physical objects that can occlude the interface. We dynamically adapt the interface layout due to the presence of the physical objects. To do so, we started from identifying main challenges. The first challenge is the efficient space coverage or the outer shape. Imagine a student Bob at a smart campus. The classroom is augmented by projecting interfaces on a table. As the class starts, the system projects a file navigation showing a grid of folders. Here, the table is circular and the projected interface is square. So Bob cannot use all the available display space. On top of that, there is a handling of object occlusions, or inner holes inside of the display area. Imagine teacher starts providing the session's instructions and Bob needs to take some notes. He opens his notebook covering a part of his interface. Bob is no more able to interact with the content below the book. Moreover, Bob needs to open a folder to access pictures. He decides to rescale his window to avoid occlusions with his notebook. The window now covers only half of the table, which leaves a large part of the table unused and makes images too small. Then student needs to carry out the brainstorming session using Post-its application. Bob starts adding and linking Post-its. He also needs to manually display Post-its to the available space that is not covered by the physical objects. Also, if he moves a book, then he needs to rearrange all the Post-its again. To tackle these problems, we propose novel solution based on two core contributions: the design and implementation of the graphical deformation of dynamic decals, and the design and implementation of a constraint-based approach to optimize the layout of decals. First, I'll present you the decal deformation model to preserve content when two decals collide. In order to deform decals, we present them as a field function. We implement square decals, square with rounded corners and rounded and circular ones. Here is the example of the content deformation of the two decals that represented as the field function. The G is the deformation operator. Here you may see the results of the deformation. We implemented 4 types of it. We make inside part either overlapped or squashed, and also we either preserve boundaries or blend them. Then we did a user study on shape deformation. The survey consists of 2 parts. The first part is the pairwise comparison. We decided to only compare collisions between decals having the same shape and content. For the second part, we made a study on the shape preference. The task was to rank the shape in order of preference for each type of the content, for icons, images, and text, and also motivate the choice. We asked 27 participants to make a pairwise comparison. We asked questions of which deformation is nicer, clearer, and more associated with the group. We did this for 3 shapes, 4 content types, and 4 deformations. We made a statistical test for pairwise comparison. Using transitivity satisfaction rate and Bradley-Terry-Lewis model, we analyzed individual consistency and group consistency. Let me explain with the example. For simplicity, I'll only show 3 deformation conditions. Let's denote the first deformation condition as A, the second as B, and the third one as C. If the participants rate 8 greater than B and B greater than C, then we expect that A is larger than C2. Otherwise, the results are not consistent. Thus, we removed 4 participants from our study due to individual non-consistency in their results. Looking only at consistent results, they show that for icons and images, participants prefer square rounded shapes, and for the text is only square. For all types of the content and shapes, it is preferred to have overlapping union deformation. Our second contribution is the design and implementation of constraint-based approach to control the placement of decals. Imagine that you have a rectangular interface as on the left, and you want to present it in a freeform shape as on the right. So what is the way to handle the content? The solution we propose is the constraint-based layout optimization. Each constraint is defined as a cost function, and layout optimization is defined by minimizing some of these cost functions. We implemented 3 constraints. The first constraint is the gamut constraints. In this case, it's overall display shape. The gamut constraint is used to keep the decals inside the display area. When the decal is outside of the gamut, the system penalizes the decal and moves it inside the display area by minimizing the cost. The next constraint is the distance constraint. The minimum distance constraint is making the decals not overlapping with each other. If one decal gets too close to another, the decals will be penalized. The closer the decals to each other, the higher the cost is applied. For the maximum distance, the system is not allowing the decals to move too far away from each other, keeping them at the maximum allowed distance. The last constraint we implemented is the alignment constraint. As you may see here from the slide, the alignment constraint is pushing the decals towards the line, so the decal has one horizontal alignment point. We made an automatic quantitative evaluation of our constraints. To do so, we measured the percentage of content preserved and the layout simplicity, and automatically computed these metrics. For this, we tested 4 interfaces with different conditions. Here are the different combination of constraints applied using our approach, where the gray disk represents a mug. On the left, we only apply gamut and minimum distance constraint, and we name it decals min. In the middle, we apply gamut, minimum distance, and alignment constraint, and we name it decals align. On the right, we apply gamut, minimum distance, and maximum distance constraints to keep decals with the same color as groups. Thus, we have a name decals group. We implemented 2 baselines, no deformation and warping. No deformation displaying condition is when the interface is simply included with the physical objects. Another baseline is warping, where the whole interface is deformed due to the presence of the physical object. As a comparison, we show in this slide the decals min and decals aligned for the same interface. On this slide, you may see the differences between warping and minimum distance constraint when applying the solver. On top, having 5x5 grid of folders and applying warping, the content is either deformed or hidden completely. This impacts the content perception. When the interface consists of 2 display areas, the middle column is completely hidden. Same we may see with the donut display shape. On the other hand, using decals min, we have all the content visible at once. Here is a difference between applying gamut and minimum distance constraint in decal min and gamut and minimum distance and alignment constraints in decals align. In the first row, the content is simply adapted to the display shape, whereas applying alignment constraint keeps the graphical elements in a specific structure. The grid of images and the grid of folders are aligned both horizontally and vertically. In the last interface, we apply alignment constraints on the toolbar. After making an analysis of data, the result shows that the dynamic decals improve content preservation and alignment. After evaluating the constraints, we concluded a final user study. The goal was to collect the feedback from users regarding aesthetics, content visibility, content alignment, and grouping of our system in a real setup. We tested 4 interfaces, and the evaluation consists of 2 parts. The first part is focused on the interface deformation by object occlusion. We conducted it on the 65 inches tabletop. We asked participants to put physical object, which is a mug in our study, on 2 different positions to occlude the interface. Then make the evaluation in terms of overall interface being nice, its content visible, aligned, and grouped. The second part of the user study is focused on perception of the interfaces in the freeform shapes, including display area split by 2 and a donut, which is a disk with the hole in the middle. This time, we ask participants to evaluate displaying condition applied on the interfaces. Here is the example of the 3x3 grid of images interfaces, applying gamut and minimum distance constraints. Participants used a 5-point Likert scale to rank their preference on these metrics. For the first part of the study, we asked participants to rank the image viewer, grid of images and folders, on the interfaces being nice, its content visible and aligned. For the mind map interface, instead of alignment, we evaluated grouping. In the second part, we decided not to evaluate grouping, as changing the display shape will have a minimal impact on the maximum distance constraint. Compared to the baseline, we obtained that decals aligned and decals group display conditions were more preferable among participants in terms of all metrics, aesthetics, content visibility, content alignment, and content grouping. We also ask participants to answer questions about system usability. We use standard 10-question Likert scale to measure SUS. According to the results, displaying an interface applying grouping and alignment constraints were chosen as the best techniques. To sum up, our studies show that dynamic decals improve interface aesthetics and content visibility, while preserving content alignment and grouping. Despite of having positive results of the system usability scale, the interaction is still limited, and only few constraints can be implemented. Also, other constraints can be added to address layout properties such as balance or symmetry. Our approach can have many applications beyond our initial augmented classroom user scenario. Here you may see the different scenarios where we applied dynamic decals. For example, a casual image gallery on the freeform coffee table, a magic desk application, a wall projection combining virtual post-it and physical postcards, a floor projection of images in a museum exhibit, a personal augmented workspace, or augmented restaurant dishware. Also, dynamic decals can be gamified. Last month, we presented it in the European Science Night for large public. We used Marvel comic characters as decals and presented the constraints as infinity stones using different colors. We named the constraints as frontier stone, visibility stone, grouping, and alignment stones. Our interactive prototype allowed people to enable or disable constraints by pressing on the stones on the touchscreen. In this example, the yellow and green are highlighted, which means that the gamut and minimum distance are enabled. Now let's move to the second part of our study of my PhD, the user-driven constraints. It addressed the limitations of previous work, such as that constraints were tested in isolation from each other and the lack of user control over the optimization. In this work, we bring interactivity into layout optimization systems, and we provide a set of spatial gestures to control layout optimization while not using graphical user interfaces. We address the question of how to bring interactivity into layout optimization systems through a use case scenario. Here is a researcher, John. His workspace consists of a combination of physical and virtual objects. Physical objects include a desk, laptop, mouse, as well as decorative elements on the wall. Virtual objects exist in augmented reality and consist of nodes, virtual documents, as well as virtual tool and widgets. John uses the user-driven constraint layout optimization tool to easily organize the virtual objects. First, he wants the nodes scattered on the wall to be aligned near the corner. However, he doesn't want these nodes to cover his best paper award certificate. To achieve this layout, he created an exclusion surface covering the certificate, followed by an attractive edge along the corner of the wall. The edge causes the nodes to move towards the corner, while the exclusion surface prevents nodes from covering the certificate. Next, he would prefer to see his non-work related to-do list in the surface in front of him, but only after closing a laptop lid to prevent being disturbed by work-unrelated activities. To achieve this occlusion-aware layout, he creates an in-view surface right behind the laptop. When John next opens his laptop lid, hiding the surface region from the view, any nodes placed where will be automatically moved elsewhere. Moreover, John likes music player. He created another attractive edge on the edge of the desk. This time, he defined a semantic attractive edge that only attracts the specific type of the content, which he assigns to a music player. There are cases where it may be useful for John to define a preference for multiple containment surfaces. A containment surface is a user defined to the region that attracts virtual content. For example, John knows that he will need a quick access to an email list and notes. For this, he creates a high priority containment surface near his mousepad. John also wants to have an additional surface on which he can situate virtual content, virtual research paper downloaded from the internet, For this, he creates a low priority containment surface on the left side of the table. The two containment surfaces now have different priorities assigned. After the research paper is downloaded, it will be positioned on the low priority surface, as the high priority surface reached its full capacity. We also envisage how user-driven constraints approach helps in collaborative scenarios. In particular, preparing a shared workspace before the collaborative activities takes place. John has scheduled a quick meeting with his colleague Sarah. He knows from experience that he'll be sitting on his chair while Sarah will be standing next to him. In this case, John and Sarah will have different user perspectives of the environment. And defining the surface on which they place virtual content beforehand can help avoid confusions caused by any occlusions. Before the meeting, John creates a camera system for his own expected perspective, and the second one for the Sarah's expected perspective. The intersection of two surfaces became the shared containment surface. Based on this user scenario and the recommendations from the previous works, we present our user-driven constraints. Our approach allows users to define virtual content placement optimization, unifies the interaction experience by considering all the constraints at once, adopts a deviceless approach based on the hand gestures, supports direct manipulation, and avoid graphical user interfaces that can break the interaction flow. In this work, we create a design space of interactive layout optimization for augmented reality environments. We conduct a user elicitation study exploring which gestures would users perform to conduct such interactive optimization. We design and implement an interactive prototype demonstrating our approach, and validate our approach through a controlled summative study. Let's start with the design space. Our design space consists of 3 dimensions: the user-driven constraints, the region of the interest, and the constraints parameters. We defined 8 different user-driven constraints. Attractive edge allows users to define the edge near which the content should be displayed. The effect of this constraint on the content follows a spring metaphor. If the content moves away from the region of the interest, it will be pulled back. Repulsive edge defines the opposite behavior of the attractive edge. If the content moves towards the region of the interest, the metaphorical spring will push it back. The next constraint is the containment and exclusion. Containment constraints allows users to define a region that will contain virtual content. The exclusion constraint defines the opposite behavior of the containment, meaning that when the user defines a region where the content should not be displayed. Another constraint is an in-view that allows the definition of dynamic optimization over certain regions, which are enabled only when they are in the field of view of the user. Preference constraints allow users to define the priority order in which containers will be used. When one region is filled with the content, the next preferred region will be used to place the content. User perspective constraint allows planning for commonly used viewpoints or collaborative activities by anticipating the intended user perspectives from the participants. The last constraint is semantics. It allows the user to associate the semantics with the region of the interest. Once we created our design space, we need to define the gestures for the user-driven constraints. We looked at the previous works to see which gestures are already used for immersive interactions. However, it's not clear which gestures define each constraint and how to reduce gesture delimiter for fluid interaction. So we conducted an elicitation study to explore the design space of the gestures that could be used to define our user-driven constraints. The aim is to identify gestures that are intuitive and easily discoverable by users. We asked participants to suggest hand gestures or the signs for 14 different constraints or the reference. We asked participants to propose up to 3 gestural signs for each referent to choose their preferred one. Here you may see the most frequently proposed gestures for each of our constraints. When analyzing the results, we discovered that similar gestures had been suggested for different reference. These differences in the hand used, for example, dominant or non-dominant hand, the number of fingers, or the combination of simple gestures, for example, tap or pinch. We can summarize our results as follows. Collected gesture set was made of variation of simple gestures rather than more complex. The selection of the region was almost always performing using the raycasting. Many gestures started with the raycasting were followed by a specific, simple, but meaningful gesture to define the appropriate constraint, for example, a containment. The interaction follows an object action model, where the user first selects the object, which is the surface in this case, and then applies an action, which is a user-driven constraint. Being inspired by the proposed gestures and metaphors for the constraints behavior, we designed and implemented a set of gestures using Unity 3D. We used MRTK core services, input system, and spatial awareness to detect hands and geometry of the environment. We then applied a distance-based approach. Thus, when combining constraints, optimization affects only objects that are within a predefined radius. We validated the use of our gestures for creating a user-driven layout optimization using a summative study. In this study, we asked participants to create a layout for 9 virtual objects. They did it with 2 different techniques, manual placement and our technique, which is user-driven constraint. Using our technique, after creating a user-driven constraint, we asked participants to rank with a Likert chart. We asked questions if the gesture to create constraints were intuitive, if the participants liked this gesture, if the gesture was easy to learn, easy to remember, easy to perform, or if it is socially acceptable or easy to use. Overall, the gestures had majority of positive score for the evaluated metrics. After each technique, be it manual approach or the user-driven constraints, we ask participants to fill out NASA TLX to measure the workload and the level of agency. The summative study allowed us to collect the first feedback on our gestures and on the interest of our approach. Overall, the gestures were appreciated and found easy to perform. Our user-driven approach was preferred to a manual arrangement and requires lower temporal and physical demands. Besides, this study allows us to test the use of several constraints in the same time. Our research revealed some criteria that people tend to apply when defining hand gestures. First, participants try to reduce the complexity of the interaction by using simple gestures. For example, if the attractive edge was created by dragging inwards, the repulsive edge was created by dragging outwards. Second, the participants wanted the interaction to be consistent when creating regions and constraints. For instance, the semantic label was added using the same gestures for all type of the regions. Moreover, our research validates our initial design objectives. For example, participants felt similar level of control with our approach as with manual interaction. This validates human-in-the-loop objective. People were able to use the various hand gestures to configure their layout without any explicit gesture delimiter. This validates holistic design and natural hand gesture objectives. Also, creating a containment surface with a direct hand ray was intuitive, as well as bimanual gesture to create an edge. Also, participants were able to define a complex spatial layout while using no menus. Our work, however, has some limitation. First, we optimize the content only within a specific distance. Doing so, it's hard to anticipate to which area the content is attached. Also, we only focused on small 2D widget to reduce the complexity. From the technical part, HoloLens 2 can only recognize limited set of gestures, whereas participants suggested more complex gestures and also outside of field of view of the headset. After explaining dynamic decals and the user-driven constraints, let us move to the next part, to the last part of this presentation, conclusion and the future work. To sum up, my PhD addressed the challenges of pervasive freeform interfaces that led us to the 4 main research questions: how to adapt the interface to freeform display areas and the presence of the physical objects that can occlude the interface, how to dynamically adapt the interface layout due to the presence of the physical objects, how to bring interactivity into layout optimization systems, and how to provide a set of spatial gestures to control layout optimization while not using graphical user interfaces. We address these research questions in our 2 complementary works, dynamic decals and the user-driven constraints. In dynamic decals, we apply the deformation model, changing the shape of colliding graphical UI elements. We also implemented dynamic layout optimization model, displacing graphical user interface elements depending on the user interaction and constraints. In the user-driven constraints, we created a design space defining 3 dimensions. We made a gesture elicitation to explore this design space. And we implemented a complete gesture set and the corresponding content optimizations. As a future work, in a short term for dynamic decal, we envision the research direction to define the interface aesthetics by developing computational approaches that preserve aesthetic properties when changing the geometry of the display shape. Also, the future work may address the implementation of new constraints. For example, the constraints to adjust the size of the decals. Also, the future work can investigate the impact of content distortion to better address the challenges of perception of the interfaces, as well as to facilitate an integration of dynamic decals into pervasive interfaces, for example, by providing a proper API. As a future work for the user-driven constraints, we consider to provide clear feedback and instructions for the gestures. For instance, highlighting the area where the gesture is applied before the pinch is released. Another future challenge will be to define the direction of the attraction while limiting the gesture delimiter and using no graphical user interfaces. Next future work would be to extend the current virtual content to other types of user interface elements, such as 3D virtual objects or large windows. Moreover, we only consider the gestures that can be performed on HoloLens too. But our study revealed that participants would like to perform gestures that are not recognized by the device. Also, developing a more robust optimization system will require to use an external solver. For example, the one that we use to optimize the placement of 2D widgets in the projected interfaces in dynamic decals. Not to mention, future works may address the non-trivial challenges of extending 2D optimization to 3D, or predicting the impact on the user performance. In addition, our 2 previous contributions to pervasive user interfaces could be combined. This combination could lead to the question of how to arrange content within one display and between multiple display areas all at once. Such a blend would benefit from a holistic and natural interaction, allowing users easily to guide the layout optimization in the real world, while preserving aesthetics and keeping the content within every region well organized. Last, conducting an interdisciplinary research and bring together different communities of the HCI raises several questions. A combination of a user-driven optimization and HCI predictive modeling approaches could facilitate the interaction of pervasive environments. For instance, fit-slow focus on the speed-accuracy trade-off when accessing UI elements. Applying it could suggest efficient content placement based on the user behavior. However, it raises the challenges of how to allow the users to understand and visualize the outcome of predictive models, how to combine user-defined constraints and with predicted parameters, or how and when to limit the number of interactions between prediction and optimization. The second challenge could be the explainable optimization that helps to reveal the internal functioning of the optimization, including the relationship between constraints and constraint regions. It needs to address the challenges of how to provide users with the appropriate visualization of constraint parameters, such as weight, without visually overloading the user's environment. Last, a version control system could be added to facilitate collaboration, since it's important to keep track of shared history of user actions. This is crucial, especially when moving from one environment to another. The future research needs to address the challenges of how to maintain virtual content organization and awareness of the other collaborators when transitioning between the environments. Thank you very much for your attention. That's it for my PhD thesis.
Thank you. So it's now time for questions, and we'll start with the two reviewers. So I will start with the reviewer just near me. So Gilles, I have a question for you.
Thank you very much. So thanks for the invitation. It was a real pleasure to read the manuscript. And first, I would like to congratulate you because, of course, a PhD is a long path, and you did it, so it's really cool. So yeah, as I said, I really enjoyed to read the manuscript. There is a lot of work that has been done. There is a design of interaction techniques, the implementation. I think it's also a lot of work. The empirical studies also are quite impressive, and it's very rigorous. So it was nice, and the presentation is very clear, very easy to follow, etc. So. And yes, the technique about the deformation of icon, it's amazing. I really like it. So yeah, so my first question is more about the definition. I would like to know exactly for you, what is the difference between optimization and adaptation? So I'm not sure I have exactly the same definition than you.
So adaptation is when we have a occlusion, the virtual content is applying some algorithms to move the virtual content, like to adapt to the environment. However, the optimization may have multiple constraints, so it's converging to one proper solution, because the adaptation may use just if-else statements, and the optimization is taking all of the parameters into account, and it gives you the optimal solution. In the adaptation, there is no optimal solution. It's just trying to adjust whatever it can.
Okay, so it's not the same definition than I have personally. I don't say that it is a good one, but for me, optimization is like you run the optimizer and you have a solution, and that's it, and it is used. For me, adaptation is more like a loop when you will do the optimization at each time. So the adaptation needs an optimization method inside.
But, yeah. No, for us, we don't use optimization inside the adaptation, because some of the work didn't use the constraints, or they didn't use solver to adapt virtual content to the presence of physical objects. So that's why they created some kind of the outlines. Let's say when the mark is on the table, they created the outline, so the content is attached to this rail, but they were not using any solvers. So let's say if they have 2 or 3 cups, the rail will not be adapted properly because the solver cannot handle all of these constraints at once.
Okay. My second question, I think I put it in my report. It's about what is really specific to immersive environment. So is it some constraint about the thesis? It is some choice? I don't think there's good or bad answer. It's just to better understand why you have this focus on immersive environment at some point in your thesis.
Well, first of all, the immersive environments becoming prevalent nowadays. So that's why we want to go with this technology. So we are kind of ahead of time to be prepared for the new technology. And we started with the projected interfaces in 2D first. So to decompose the problem into smaller sub-problems. So that's why we first made some contributions in the flat freeform displays, and then we moved towards the more complex environments, which are immersive in this case. Otherwise, it would be too complex to run everything and to have some ideas or to have some challenges, to understand the challenges in the immersive environments.
Okay, so at the beginning of the thesis, you have already decided to go in direction of immersive environment.
Well, I think it was evolved like during the thesis. In the very beginning, we didn't think to go. We were not sure if we are going to the immersive environments or not. So the first part was using the projections, and then we realized, okay, so maybe we can try to apply these methods into immersive environments because now they say quite useful.
Okay, thanks. Yes, on the first project, yes, we can see here. So I was wondering how smooth it is, the animation. So it seems it's a bit like a step-by-step, small step-by-step. When we see it, tuck, 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 slightly. I was wondering if it can be smoother, if there's some reason, if it is just the power of the PC. Or...
Well, the PC that we used is quite powerful. And yeah, there is a small delay. So to remove this delay, we could use the graphical, the GPU, for example, like do all the calculation on GPU, because the deformation itself require a lot of computational power. So, and using just the CPU, it's not enough to do the deformation calculation every frame, because whenever we move the Mac, whenever the interface is changing, the system updates the frame and it updates the field function that I talked before, and then applies the UV mapping of the image to this field function. So it's very computationally heavy approach. So if we remove the deformation, the solver works fine. So it's like it's very smooth.
Okay, and if you move the cup much faster, it really.
I think sometimes it's not pushing. It's kind of it slips inside, and then the decursor stays. Maybe it will go like the other direction. Yeah.
Yes, I was wondering also. Answer one question. Yes, did you for the first project again? Did you try to just ask users how they will organize this icon by themselves? So you move the cup and you ask them put the icon exactly as you would like to. How user will spontaneously organize these different icons. So currently, what you did is the users, if I'm right, you show the results and you ask the user how they evaluate it, how good it is from their point of view.
For the last user study, we showed the results. So the last user study was consisted of two parts. The first part is the dynamic, and the second part is static. So for the static, we showed them the interface and asked to evaluate the interface in terms of it being nice, aligned, and grouped. But in the first part, when we asked users to dynamically move a Mac towards to the interface in two predefined positions, so they see in a real time how the interface is changed.
Yes.
Is that your question?
No, not exactly my question. I was wondering, so you put the cup somewhere,
yeah,
and our user, if they was completely free to move the different icon, how they will organize them?
Oh, we didn't ask them to completely like to freely move the content.
Yes.
So we had the content that is already organized. Let's say for the 3x3 grid of images, we already put them as a grid aligned horizontally and vertically, and then we ask user to move the Mac on top of it, like over the interface, and then to evaluate the condition.
Yeah, but my question is, will it make sense as a future work to ask user how they would like to organize the icon by themselves, and to see after if there is some algorithm and some constraint where the objective is not some kind of absolute aesthetic, but to see how close it is from what the user spontaneously will
exactly. Do. Yeah, so that's why as the future work, like predictive models can
This
can
is called
address
predictive
this.
model.
Yeah.
Okay. Yes, also for this project, I was let me know when I should stop. Okay. So currently when the two icons are colliding, will it be possible to consider to have some part of each icon with different weight so that the deformation will be different within the icons?
Yeah.
So the idea is that if you have a face, for instance, which will be no deformation or almost no, and some part will be with more deformation.
Yeah, it's possible. Just we need to change the field function. That is, as you remember, I showed you the blue images of the rectangular and rectangular with rounded corners and circular. So these we just need to change these functions, and depending on which one has higher weight, well, depending on the weight, we can change the field functions, and that's how we can preserve one one decal like colliding deforming too much, and the other is like staying as more or less as it is.
But you can do it in some part of one icon?
It will be, I'm not sure if it can be just only one part, but from what I understand, the field function is the solution. So depending on how to define the field function, you can do anything.
Okay, cool. Yes, and also on this project, I was wondering, yes, I would like to combine both, of course, the first one and the second one. Yes, I was thinking about which kind of about multi-touch gesture, because it's on the 2D plan. I could do to say, okay, just move this and not this. So I would like to maybe to hear more about you, about what you would like to do if you have more time on this combination.
Yeah. So in the second project, user-driven constraints, we use the gestures to create to optimize the content placement, and we created the regions, let's say the edge or the containment, the surface. And the future research should address the question of which gestures we can use, not only to place the virtual content inside of these regions that we did in our second work, but also how to organize the content inside of each of the container, each of the surface. So maybe, let's say when participants created the edge, the attractive edge or repulsive edge, they did like these gestures, like moving inwards or outwards. Maybe something similar gesture will be applied to make the alignment. And also the question is, do participants need to look at the surface once they apply, or is it kind of predefined, or is it applying only to one surface, or is it applied to all the surfaces at once? So the question is basically how to, on top of what we did in the second work, how to add more gestures to organize the content. That's the hardest part.
Okay. And for the second project, my question is, it's not so clear for me if or how you control the weight of each parameter. So how attractive is a line, for instance?
Okay, so yeah, maybe I didn't explain it here. So the edge is created by doing the pinch, and we have two thresholds. So the first threshold defines the direction. If we move a bit inwards, meaning that it's attractive edge. Okay. And once the edge is created, then there is another threshold. If we move outwards, it changes the width of the edge, like the radius. So, and the width is representation of the weight. Okay. If we want to make a repulsive edge with very big weight, so we just do we do pinch, we do outwards. Once the repulsive edge is defined, we move forward to make it like also thicker. and the thicker the edge is, the more weight is.
And what's happened if you have an attractive edge close to a repulsive edge?
With this setup, I think we didn't try it, you know? I think no, I think it depends on the distance, because the weight and the distance is different thing. So because we applied the distance-based approach, and once the content is repulsed from the repulsing edge, so it's no more under the influence of any constraint. So, and after it's gone, so there is no way to attach to the attractive edge. So I think it will just repulse, and that's it.
Okay. So thank you very much, and again, congratulations for your work.
Thank you.
Thank you. So it's time for the question for the second reviewer. So Wolfgang, it's yours.
Thank you. Thank you. And please, Maud, if I speak too long or ask too long, please feel free to stop me, right? I mean, I'm not exactly sure how your protocols are, and so please let me know, okay?
Yeah, I think you have time for a question. I will interrupt you if it's very long, but it should be okay.
Yeah. I just try to make sure that I conform to protocols as you use them, right?
Yeah.
They're not quite the same across the
no
planet.
worries.
So, Aziz, many thanks for the presentation. It was a very nice presentation. I also like your thesis. I mean, this is well written, so very interesting work. But as I'm an examiner on a committee, my job is to be critical. Okay. Now, Gilles already asked some interesting questions and stole one of my good questions, but that's all good. that's just fine. So I will start, of course, with the first part of your work, the dynamic decals, right? And one of the things that showed in your presentation, you used a distance function that has discontinuity, especially for the rectangles, that has a discontinuity at the corners. As in, the distance function is not smooth. And if you can go maybe back to your slides, where you showed those distance functions, you can see that those distance functions are not smooth. Right?
In the first work, right?
Yes, in the first one. Yeah. You showed that image of how the distance functions look for the three different rounded rectangles and
If I'm not mistaken, you are
no, even further back. Yeah, here, this one. Yes, yeah. So on the left side, right, you have these the corners, right? They have basically, you have these discontinuities in there in the gradient, right? In the corners. So I've used distance functions in my work, and I've observed that discontinuities in the distance field usually cause problems. So I'm asking you, do you have any problems because you have these corners affecting your optimization and everything, because it's not smooth there, the function?
Well, so here, well, basically it's not a distance function. Well, it's a distance. No, it's a field function. Because
people call it a distance field, distance function. You know, different names, same concept. Yes.
Okay. Well, no, for us, we didn't have much of the problems with this. No, I can't remember that we had some problems.
Well, I think if you go a few slides further, you had actually images. Keep going. Yes, here, stop. You have actually those things flowing together a little bit too early, which may be an artifact. Actually, was it this slide? Not this one, sorry. Can you go one further? I can't remember what the slide exactly was. The one with where you had the teddy bear. Yes, this one here, right? Okay. So there's sometimes a little bit interesting artifacts that happen on the right side, right? Yep.
Yeah. Yeah, we have a bit of artifacts here. Yeah.
I believe that this may be the source of your artifacts there.
Yeah.
And that's directly related to your choice of distance function, right? So I just want to highlight that, right? Because you're basically in the code, you're assuming a smooth function, but your function is not as smooth as it is, right? And that creates artifacts, right?
Yeah.
I just want to highlight that you have a cause there, and it may be interesting to actually specify that, right? Because then it explains better what actually is happening.
Yeah. Okay. Well, thank you for noting this.
So your interface for the dynamic decals is interesting, but what happens if there's not enough space available? And that always happens in real world, right? You always have either too much content or you have too much clutter, right? As in too many objects on your table. So what happens then? Oh, hello? Run out of battery? Or muted? Whoops. It's all good. Technical issues, all good.
Yeah, wait. So we have, seems that we have a little problem with the sound of the room, so it's coming.
Helen, come please.
No, it's not the Zoom, it's the room.
Yeah, I know.
Sorry, we have a small technical problem.
No worries, it's all good.
C'est pas le Zoom, c'est la salle qui se éteint. De la salle.
Ah, okay.
Yeah, but it's advanced in understands.
Ça dit rien, mais c'est éteint tout seul. Ben, c'est bizarre, il y a une utilisation qui est pas sérieux. Ouais. Dans un certain temps, mais c'est pas sérieux. Ah, c'est ça, c'est parti. Le son, c'est piloté, hein.
Maybe the simple solution is if Aziz uses the hand microphone for now until this issue is resolved.
The microphone of the room is turned off.
Yeah, all the audio system off. Yeah.
Oh my.
Okay,
I think it's just going to restart the room. Okay.
The robotics overlords have decided that we can't continue, right?
Yeah. Just restarting.
Okay.
Yeah, there is no way to change to restart just the audio. So we are starting everything.
Well, I mean, if it's only like that, maybe if I put the sound here, isn't it fine? No? Okay, let's.
Yeah, okay. How long did it take? A few more seconds to turn it off and a few more seconds to turn it.
C'est absorbant.
Ah.
Oui, je peux regarder.
Avec un tu mets un truc qui bouge, ça te capte directement là.
Pas qui bouge, c'est bon, ça se fiche.
Okay.
I think we're back. Yeah. So it's cool. Thank you. Yeah. Sorry for this issue.
No worries. I mean, look, so now I know in roughly an hour we expect this again. No, it's all good. So let me ask the question again, because obviously things happened here, right? So what happens when you have too much content or not enough space, right? And users always have too many files, or conversely, you have too much clutter on your desk. What happens in your system then?
In the current setup, what happens is that the decals are deformed. Like most of the time, they are like too much deformed. But if there is no way to contain all of these decals in the place, they're just going outside of the windows. So that's a drawback.
Okay.
So that's why the additional constraints, such as to reduce the size of the decals, should be introduced as the future work.
Okay. So you're starting to think about that, right?
Yeah.
Because that's I mean, it's something that's always happens. That's what I call it, right? I mean, give your user a hard drive that has 200 megabytes and they will fill it up, right?
Yeah.
Or 200 gigabytes today, more accurately, right?
Yeah.
They will always fill it up, right? So one of the constraints that you have used images and so on, and some of the content that you're using scales well, right? So an image you can make smaller, but if you have a decal that contains text, you have the problem that you can't easily make the font size smaller because then you can't read it anymore.
Yep.
So any thoughts on that?
Yeah, we have to make a constraint that prevents to scale it to to put a minimum scale. That's the first solution. The other thing we can use, I think Marcus works of how to adapt the text to non-rectangular shapes. So basically one of the solution could be just present text as one long line and then to cut it to put a new line whenever the shape ends. There is no other solution I can think of to preserve the text if there is no space, except for maybe putting a kind of an icon of the text, so people don't have tons of information that is not even understandable. So maybe put an icon of the text, so when the user clicks on it, it expands. So it kind of I think it makes sense to see what happens after.
Okay. So you're also using a solver, and I've used solvers myself in various pieces of my work. So what if the solver doesn't converge or doesn't find a solution? What do you do then? Have you run into that problem?
In dynamic decals, I think we didn't have such problem because the problems are too simple. In the user-driven constraints, I think somebody's
nice balloons.
I think is doing like this, and it's sending the bubbles.
Audio, the audio. Okay.
Okay. So for the user-driven constraints, the solver is not converging at all because we are using the native MRTK solver. So that's why when we're using the distance-based approach, the content is either moving to one region or to the other if the content is under the effect of two constraints. So there will be a jitter. So there is no convergence, unfortunately. So that's why we need to implement another solver like we used in dynamic decals. So we think there is a need to add an external solver to overcome this issue.
Yeah. No, so this is a general issue, and I asked this question because it is a general issue with solver-based approaches. Is basically the system is doing some magic, and if the magic works, great. If the magic does not work, what happens, right? And that's a general issue with solver-based approaches. Sometimes you can constrain the problem well enough that you don't run into this issue, but sometimes you don't have that luxury, and then it's interesting to actually think about what happens, right? Sometimes you also get multiple solutions from a solver, and you need to make a decision. And typically you do that based on the objective function, right? But sometimes you have solutions that are very close together and basically indistinguishable, right? So there's all the other issues that come with solver. So following up on Gilles' question about, so the face, you may remember his question about when he said there's a face in an image and you shouldn't touch the face, but you can squeeze the rest of it better. Your answer was that you can handle this through the field function. I will point out that there's other approaches. For example, there's the seam carving approach, which allows you to resize images and carve out seams of images. So that there are other approaches, and you may want to look into that, because people have thought about that problem. And yeah, there's other solutions. I'll just point that out, right? And
thank you.
To do this. And you in your user study, so now switching to the user study for dynamic decals, you used the simplicity metric.
Yep.
For the layout simplicity metric based on previous work. How do you know that this metric actually captures the right thing?
Can you repeat, please?
How do you know that this metric, simplicity, actually covers what we humans mean by simplicity?
Well, first of all, I think it's a really good question. But first of all, we relied on the related works that addressed that explained what simplicity is. However, for the circular screens, for the circular display areas, the simplicity may differ. So let me. Okay, well, never mind. So yeah, so for the circular screens, for example, the simplicity may mean not a line, but kind of a ring, or like putting the items within the specific radius to form another circle. So to address this issue, to understand these metrics, we tried to have another project, but we were stuck in the middle because we didn't have any knowledge of this. Because there are metrics such as balance, for example, and in the, let's say, symmetrical display shapes, we can apply balance. But if it is a freeform shape, it's really hard to find the balance. So it's very subjective. So that's why we kind of gave up on this project after dynamic decals.
Well, the Gestalt perception in general is something that we partially understand quite well, and partially don't understand so well from a technical point of view, right? We can, as you say, balance. In some cases, we can characterize it fairly well. In other cases, it's a really difficult problem, right? And similarly for the simplicity that you're using here as a metric, please, I encourage you to also point out the limitations of what this metric can do and what it can't do, right? Because you're basically using it to judge the outcome of your user study based on a method that doesn't really capture perfectly what simplicity really is in a human sense, right? So the term is a bit overloaded, and it would, I think, be a good thing to actually characterize, to state that outright, to say, within the limits of the simplicity measure, and here are the limits, right? Here is how we characterize that, right? Because otherwise it comes across as too general as a statement.
Yeah,
right?
Makes sense. Yeah.
Now let's switch to the 3D. And you already alluded to this, and this was one of my questions. You have, of course, lots of magic parameters. How far does the influence of an edge extend, right, is one of these. How strong is it, the influence, and all of these things. And clearly, at the current level of your user interface, you can't adjust that easily. Well, maybe you can. You define an edge, right, and it's an interactive edge, and then you move further away to show this is how far it extends, right? So, because there's lots of magic parameters behind this, as far as I can see, right? And so this is something you may want to also make explicit, that it works in this current system for this current setup, right? But if you now take it into a larger room, you most probably have to tweak a lot of things, right?
Yeah, exactly.
Right.
Yeah, that's why like I said, the future research has to address these challenges as well, to understand to predict the user behaviors, and depending on the context, for sure, the virtual content has to be adjusted to different environments. And I think Barrett did this work to move virtual content and to keep the layout within different environments.
Yeah. I mean, the user behaviors are a separate issue, and we'll talk about them a little later. But you have to adapt the system to the content, to the layout, to the physical space, right?
Yeah.
And there needs to be some way to do that. Right? Just a comment here, because you already talked about the MRTK solver and all of that. You're basically looking at hierarchical solving, right? Because you're now solving within the region, right? So that's a hierarchical solving approach. There is known approaches for that. You may want to look into that. And as far as I can tell, your choices, your implementation choices, also for the AR-based project, were limited by what the solver can do. Can you elaborate a bit on that? How much did that influence your design there? Basically, that the solver is not ideal. Let's put it that way.
Well, I think the first limitation was the time, because and the limitation of the solver affects the combination of constraints. If we test only one constraint at a time, we don't have any issues, right? And the limitation was in time, because we submitted this paper to Kai, and we had only 5 weeks to make another user study to combine the constraints. So definitely, if we had more time, we would have used another solver to converge to some result. So that's why here the main limitation is the combination of the constraint regions. So for example, we wanted to check to test the containment surface, and also, let's say, applying the attractive edge inside the containment surface.
Yes.
So in this case, it's really difficult to do it. So that's why we were limited in combining kind of hierarchical optimization as well.
Yes. So, yeah. So I mean, it shows for people who know about solvers and how they behave, right? It shows through that some of your choices are clearly mandated by what the solver can do and what it can't do, right? And it may be good to actually make that explicit, that some of your design choices, right, in the user interface design and what you support and how you support things are actually due to the technological limitation and not to of a specific solver, and not to the general idea itself, right?
Exactly. Yeah. So for the second part, we were very limited in terms of the combination, and also we were limited a bit on the user study in terms of the environment. So that's why we made the user study for the user-driven constraints split in 2 parts. So we had to remove. So once we applied some of the constraints, we created some of the regions. Then we had to remove them and to apply another constraints on the same region, on the same physical environment. Yeah, so that was also a bit on the issue.
All right. You had the collaborative interface where there's Sarah. I believe Sarah comes in and looks at the. Can you just pop that image up on the? Should be a few. Yep, here, back, there. So what you point out is very interesting, but one of the things that when I saw the images, I was like, so in general, you will see that if John sets his eye level, that may not be at the right eye level for Sarah, because Sarah may be not quite as tall as John. What happens?
Well, John has to know it in advance. So yeah, that's
okay.
kind of...
Yeah. So I just want to point out that I mean, the idea is not bad. I'm not saying that the idea is bad, right? But I'm just pointing out that you implicitly make some assumptions here about visibility from one person's viewpoint that may not hold for another person, right?
Yeah, for sure. I mean, it's a good question, and what we didn't implement in this work is the alteration of the regions and the constraints. So we only created the constraints, and there is no way to adjust them. So, for example, when we create the camera frustum, let's say when John's create the camera frustum for Sarah, so ideally Sarah should be able to adjust it, and then the effect on the final results on the intersection of two surfaces won't be that much. So that's why anyway, if John miss a bit the height of Sarah of Sarah, so it won't affect that much of the overall result.
And you're right about that, right? But you're also implicitly assuming that you know who else will view it, right?
Yeah.
For example, if I now bring a 6-year-old child in, that's a substantial difference in height, right?
Yeah.
Right. Well,
exactly.
let's not get into the issues if they should actually put the augmented reality headset on and the interpupillary distance and all of these little issues that come with that. But so I'll not talk about that here. Right? But just recognizing that. In your work, you point out this is an augmented reality interface, and I fully agree. You know, this is actually that this is interesting. I will point out that what you're doing is using a lot of 2D surfaces. Okay, the 3D aspects of your work are very small. Okay, I'm pointing this out as a clarification, not saying that it's not 3D at all, but I'm just pointing out that it's mostly 2D. It's a space that I call 2 point something.
Okay.
D, right? 2.1, or we can debate now if it's 2.1 or 2.3, but it's not full 3D, right? Because you're very strongly surface bound, and you're very strongly bound to visible surfaces.
Exactly. Yeah.
Right.
Yes.
So you're not talking about under the table, right? On the surface of the table.
Well, the in-view constraint could address this. A part of this has to go like under the table to create the surface, so it's quite weird. Yeah, so mostly we are focusing on 2D containers. Yeah, and like 1D edges. So and also
And that's fine. I'm just trying to make that more explicit, right? Yeah. Also for clarity, to say, well, this is what it is, right? And I mean, it's not a full 3D user interface where things float in midair and things are hidden behind each other and so on, right?
Yeah. Yeah. Also, we thought to present the virtual content in the midair, but the gestures are getting even more complicated, because how do you differentiate between creating something with your hands or like with your hands just next to you in the midair, or with the ray casting somewhere far away from you. Yeah. So this is also another question for the future research.
Yeah. And you just alluded to gesture recognition. So one immediate follow-up is that I encourage you also to talk about. I mean, you do talk about somewhat about the limitations of gesture-based interfaces, and you allude to them a lot, right? Discoverability of gesture interfaces is a known problem, right? There's no feedback if the recognizer doesn't recognize something, how you should change the gesture, right? Yeah. That's not a hallmark of a good user interface, I will say that, right? The accessibility of them is not great, and the reliability of them is not that great in general. And you alluded to that, right? I mean, I usually demonstrate it this way, right? If you ask people to do with a HoloLens to do a pinch in midair, a lot of people do, and I'm on purpose doing it towards the camera so you can see it, but I can't. This is their first pinch.
Yeah.
Right? They pinch like this away from the camera, and the camera can't recognize it, right?
Yeah, that's another issue because during the user studies, I specifically said participants that the gesture, the pinch, has to be within the field of view of the HoloLens. So do not occlude the pinch with your hand. Yeah.
Mm-hmm.
So, and sometimes participants were very comfortable with these gestures, and for the other participants, it was too hard to make a pinch, and it was also a bit of limitation for the user study when we performed 2 hands gestures and 1 hand gesture. So sometimes when they created the string, the edge, the HoloLens didn't recognize 1 hand, and instead they created the container. So, well, yeah, that was another issue with gestures. Yeah.
And thank you for pointing that out, because I mean that's also my experience, and having done lots of experiments in this domain, right? It's they are good for some things, but for other things it becomes very challenging. Yeah. And I just got the Meta Quest 3 and similar problems again, right?
I didn't try it yet.
Yeah, I just got mine yesterday.
Okay.
I will finish with a more critical question, and this question may make your supervisor laugh. Okay, so warning. And I know that I'm going to ask a very critical question. Okay, so why really post-WIMP interfaces? Now, clearly there's a novelty effect, right? I mean, one of the things that happens is you show people a new interface and they go like, "Oh, cool!" Okay, and that there is all good. Okay, but I believe there is also an efficiency component to user interfaces, how effective they are, right? And I believe that your supervisor has done some KLM modeling and GOMS modeling of user interfaces. So I'm wondering, and that is very much on the efficiency side, right? So how efficient, how effective are these interfaces when you think about it from that direction?
Well, it also depends on what we are comparing to. And if we are comparing to the command line interface, for sure it's more efficient. Well, I don't think I can answer this question about the efficiency.
I know. I mean, this is a setup. Okay, to some degree, it is a setup. I will acknowledge that, right? But I will point out that if you look at how long the actions take, right, and so on, and you think about modeling this stuff, you end up with interfaces that don't compare that well with some of the interfaces that we're used to, right, like the smartphones and mouse and keyboard, right? Now, clearly, so I'm pushing a little bit and saying, well, there's the novelty effect, and what happens once the novelty effect wears off, really, right? So I'm just, you don't need an answer to this because it's a difficult problem, right? But I believe I will stop here. Thank you.
Thank you so much.
So thank you. So I will continue the question with my questions. So first of all, thank you for the invitation in the jury, and also congratulations to you for this very nice work. Like you did, like a very nice work, like in the field of HCI, but you also took advantages of computer graphics methods, and then you had to understand both scientific challenges, and it's great that you were able to combine this, because at the end it was something quite original compared to other approaches. And you also did like 2 very interesting questions, because there are scientific challenges inside, but also there are like technological challenges, like using AR, for instance. It's still very challenges. And also you have like nice evaluations, and we all know that is very time consuming, so it should be underlined this. So I have some questions of course, already like a lot of questions have been asked, but I have some questions. Some of them are open questions, so I am not expecting any good answer on that one. First of all, I would have like a computer graphics questions. So you are not putting like a lot of details on the computation time performances in your, for I would say like first in the first contribution. Also, we are speaking about collision and collision detections and like our deformations. And I guess your system have some limits. Did you do some measurements or like
The measurement of performance.
Yeah, computation time performances, because I guess you have like a limited number of decals that you could put all together, and the number of collisions that could be done all together is something that you measured or not at all?
I think we didn't do it. We didn't measure the completion time because the goal was to understand the perception of the content and not evaluate the performance of our method.
Yeah, it's somehow related to the questions that Wolfgang asked. He asked about like when you have like too many decals or like not enough space, but it's somehow related also with you.
Oh yeah, I mean if there are too many decals or the space, no, let's say the space is too small, maybe the solver is still fine, can do it. But if the space is large and there are too many decals, for sure, with the current implementation, it will be quite laggy. So it won't be, let's say you can't have, let's say 100 decals. I mean, you can, but it will be too slow to compute the collision of each decal. And it won't be interactive in the interactive frame.
And would it be possible in that case, like just because like the user don't know in advance that yes, he will have too many decals for instance, in his window, and then for instance, it would be possible to optimize a little bit the performances, like saying we are not obliged to compute all the collisions at all time.
For sure, that's possible. And in our implementation, we already run the deformation only on the decals that are in the process of collision. So let's say if some of the decals staying, let's say on one side, and they are not affected, they are not moving to each other, the deformation is not applied there. So so the algorithm runs and it's only checks for the decals that are too close to each other, or the one that have a higher cost. And we only apply the deformation there. So let's say if one decal is close to the display boundary, so first of all, the optimization, the solver is moving it outside of the display shape, but then and then if there is another decal next to it, so it runs through the deformation process, and the other decals are not affected. So it's already kind of reduce the number of iterations to increase the performance, but it's still not enough. So because I still think that the algorithm has to be rewritten, like it has to be changed to increase the performance, and maybe it makes sense to put all the computation to the GPU, because in GPU it's much faster.
Yeah. Then I have like an open question, because when you are deforming object at one point they can break.
They can
break, like you will have fracture on your for instance, if you want to break your decals, like because there are two deformed, is it something that could be possible?
So you want to
how
break
you implement it?
two decals, two parts?
Yeah.
Interesting. Never thought of it.
Yes, this is an open question.
No, it's interesting. Yeah. So you're asking the way of implementation, right?
Yeah,
I understand.
like if
Yeah, so
it would be useful, or do
yeah,
you see any possibility with that behavior?
the use case or the implementation?
No, the use case.
The use case, okay.
This is an open
Well,
question.
if for example, it can be applied to the picture, which is quite large, and so now we are kind of decomposing the interface elements to decals, and we can do it the same with one decal that contains an image, and so basically the image will be like a puzzle, and we can also use the optimization on these small like puzzle pieces, and if there is not enough space, we can deform just, let's say, only part of the decals that contains in the same image. So we are not deforming. If it is one big decal, we are deforming just the let's say one part. But if we decompose it, so we can readjust it a bit, and so the deformation applies more or less evenly to the whole image rather than on one part of the image. So that could be a use case.
Yeah, it could be very, very nice. Then I have questions on the second contribution. We all know that it's quite difficult somehow to recognize all these gestures when you are in AR, and I had like several questions on that. And the first one is, did you measure the learning effect of the gestures, like the learning effect,
Yeah.
like if people were able to learn the gesture, because like depending on the number of constraints, you will increase the number of gestures, and you can, so like some users could be lost with all these gestures. They have to learn. So is this something that you already?
Yeah, we.
And also, yeah, my question was, because you have like people that know how to do 3D gestures, and some people that just are non-experts, so they don't know anything. And
yeah, definitely. So when doing the summative user study, after performing every gesture, we ask participants to feel the Likert scale, and we ask the questions of if it is easy to remember as well. So maybe you can see here, like in the middle. So we have easy to remember, and so only here for the preference, it was not that easy to remember because maybe they didn't associate it with something. For sure, if you have much more gestures, it will be harder. But also, I think that with time, when you use these gestures over time, it's quite easy to remember all of them.
yeah, because you said that you were not you did not measure like the time for doing in your user studies, the time for doing the task, but at the end, at the beginning, they should hesitate between two gestures to do what they have to do.
We didn't measure the task because after each gesture, we ask them to feel the Likert scale. Yeah. So that's the only reason. So that's why we can't really compare.
Okay. And did you see like a modification in the answer? Like something that's different? Like
what
it could be improved, for instance, to the question, easy to remember?
I didn't get the question.
Did you see some differences between the different tasks to the answer to this question? Easy to remember, like somehow to measure this learning effect. No, but if you
don't think so.
Data,
yeah. Well, maybe they remembered not the gesture, but they, over time, per participant, they were more comfortable to use the gesture, like to use the HoloLens in general, because they were more confident in pinching. Because maybe in the beginning they were struggling to perform the gesture that are recognizable by them. And for sure, over time, once they, as I ask them to create the other constraints, for sure, at least the pinch gestures were easy, was easy to perform. But regarding the gesture itself, I don't know.
Yeah. No problem. And then in your slides, you said at the beginning that you focus for the gestures on the fluidity.
Yeah.
And then my question, like you wanted to have like fluidity of each gesture.
Yeah.
But what about fluidity between gestures? And this would be related to the second questions, like how. But then first, like what about transitions between your gestures? Somehow, like I think Wolfgang already address a little bit.
I don't quite understand what do you mean between gestures, because for me, once they perform the gesture, let's say they created a region with the constraint using a gesture, so they released the pinch at the end, and the gesture is finished.
And then how do they know that?
Yeah. Oh, because they have a visual feedback once they create any constraint. So at the runtime, they have a feedback if they are creating the edge. So at the same time, they see that the edge is being created. And if they draw the surface, so maybe it's at the...
No, my question is like, okay, if you are done with this and you want to have like a fluidity with the next gestures, like doing it.
Oh, I see what you mean. Okay.
Maybe I will ask the next question because it could be related. You did not speak a lot about like sensory feedback, and you said, okay, there is like visual cues to help the user to understand what he's doing. But what about like, for instance, having like audio or haptic feedback? Could it be helpful, for instance, for these transitions between gestures?
The audio can be helpful. The haptic, I mean, yeah, for sure, both of them can be helpful, but it for the haptic feedback, it requires another device, maybe a glove or something else. For the audio, it's very easy to implement just using the HoloLens speakers.
It's just like a question of amount of feedbacks that you would like to put to the user to ease the process.
Yeah, for example, when you start the gesture, when you end it, when you start creating the region, or when you finish, you can provide another feedback, so people know without even looking at it. But I still don't really understand how to do the transition between one gesture to another. So let's say I'm finishing this surface and I'm releasing, meaning that I finished. And then if I'm doing another surface, I'm just clicking and I'm drawing again another surface. So, and I think your question is how to transition between one gesture to another.
Yeah, because as we said at the beginning, I mean, we all know that gesture recognition is not like very accurate. So somehow, sometimes we are pinching several times just because it's the doesn't
Oh,
work.
I see what you, okay.
And you don't know, for instance, if you are like finished, you are done with what you want to do, and as a computer doesn't know. So
yeah, I see.
So if you're just like trying to do it again and again.
Yeah, it happened a lot.
It's a very difficult question to design this.
Yeah, it happened a lot actually during the user studies, when participant clicked, and so something happened and they created very tiny surface, and it was very hard to delete it. So they thought they didn't do it, but accidentally they clicked on it and they just released it. So basically it's the system recognized as just maybe like 1 pixel surface. So there is no way to access it as with the raycasting. So for sure, then when you start the click, so it really makes sense to put not the visual, because in visual feedback won't work here, either the sound or or the haptic feedback, which we didn't really think.
Yeah, but
Yeah,
that's just
point.
like an open question also. Like there was like several perspective for your work. So I think it was my last question. So thank you very much for the answer. So now it's time for the supervisors.
Okay, thank you. So well, first of all, I want to thank the jury members for being in this PhD defense. Wolfgang and Gilles for reviewing this work. So it's really nice from you to take the time to read and give your very valuable feedback. So I took a lot of notes of all your questions, and I think, yeah, that's it's going to be part of our future work probably. So I also hope that we'll be able to talk about this maybe in a conference or at another time. So I also want to thank Hélène for helping with the PhD defense, with the streaming of the Zoom and so forth. So it's very nice from her. And well, I don't have really questions about your work because I know it quite well. But I'm just gonna comment on this PhD. So we met each other 4 years ago when you came for an internship.
4.5.
4.5. Okay. When you came for an internship.
Yeah.
And then, and so then you accepted to do a PhD here. And I think it was a very challenging PhD. And it's been a very challenging PhD for several reasons. The first one being that you started your PhD just before the COVID and the first lockdown. So basically you spend the first half of the first year of PhD in lockdown. And I mean, I know it must have been hard to be in lockdown when you're not in your country. You're in a foreign city, and I think that really at this time I was impressed that you were able to stay focused in your work, and you really you started the dynamic decals at that time during that lockdown, so it's really nice, and I was really impressed by that. Then there was another challenge, is that you were going to be supervised by different PhD supervisors who didn't know each other actually, and so that's always can go well or it cannot go well. So in this case, it was good, but we first had to learn how to talk each other's language. Like I had to learn what computer graphics was, and they had to learn what human-computer interaction was. And basically, that's also the third big challenge, that your work was at the intersection of HCI and computer graphics, and you had a background mostly on HCI. So you had to learn what the field function, distance function was, how to implement that, how to render all these. So not just using some graphical user interface libraries. And so you did that, and you reached that goal. It was really impressive. And then you for the second project, so you said it at the beginning, but you did it in collaboration with people at Monash University. So you spent 4 months.
Yeah.
4 months in Australia. Last 1 year ago, and that was also challenging because you were one of the first students to go to Australia after the country was closed, and basically there were a lot of issues with the visa, with the medical certificate. You had to do several hundred kilometers to get a medical certificate to go to Australia, and so you also managed to handle that and to reach Australia and to make some new collaboration with new people like Barrett and Tim Dwyer that you didn't know, and which ended up being your second project on a Kite paper. So that was really nice. And so I think that if you look at this with the perspective, you see that you have gone through all those challenges. I mean, it could have been a very difficult PhD, but you managed to, with perseverance and patience and willingness, to reach your goals. So you managed to reach the final goal, which is today you are presenting your work. So so I'm very happy that you're able to do that. And so be confident on what you're doing and on your decisions, because you are capable of doing all this. And also that I want to stress out that your work has opened the venue for future works. And we have PhDs who are already starting on some of the perspectives that you cited. And we have projects, we are submitting grants based on some of the perspectives that you cited. So your work is not finishing today, it's the beginning of other works that are going to continue in the future. Yeah, so I'm very happy, and it's been really a pleasure to supervise this PhD.
Thank you so much.
Okay, so I will also thank the jury to be here and for the hard work already done. So again, I have no questions. Just a few words. So obviously, I completely agree with all what Marcos said already. And just a comment before giving my thought. They had a lot of questions on Aziz's second contribution during the this defense. And well, obviously, they are all very good questions. And just to give some context about this second work, our first idea was actually far more ambitious than what Aziz presented, but we actually went short in time. And so we decided to reduce our expectation to basically focus on having something to propose, a proof of concept that was advanced enough to be validated by experiments. And so obviously when you do this, it clearly leaves a lot of questions open. But when you get published on this kind of project, it has a very good side, is that it always opens a lot of rooms for several new research, which is also a good thing, because then people have a lot of question about what you did, and then they may want to investigate around. So that may be great. Okay, so then Aziz, you actually started with 3 supervisors, one in HCI, one in geometric modeling, and one in geometry processing. If I'm right, you had a HCI background. And the first project you had to do was to work on content organization, including user interactions, maths for combining field functions, and maths for defining and solving placement constraints, right? And so I'm very happy that with all of those, you did not just run away, right? I mean, you just stayed focused, and actually somehow you managed to get some results, to have the system work. And it was very, very hard programming work. I mean, Aziz spent months and months programming to have everything working. And finally you succeed in it. So congratulations for this. And actually maybe somehow you enjoyed, because then you did a second project again with constraints, right? So you did not even be scared with this. And okay. And also it is known that more supervisors, well, it means more troubles for PhD students, right? The more you have supervisor, the more it's complicated for the PhD student. And you had 3, so it's quite a lot. And somehow you had the ability to navigate between all your supervisor recommendations, and finally you always propose effective solutions. And I think this is not easy at all, and I would again congratulate you for this. Okay, and the good thing is that you also introduced SCI to Nicola and me, that we actually didn't know at all before. Well, we know the word, obviously, but nothing about the science. And I would thank you for this, because now we're gonna continue work with Marcos, and we have some project that should start actually in the coming months. And there is clearly now a link between computer graphics and HCI in our lab, and actually you're part of what happened. So that's great. And yeah, to conclude, just congratulate for all the nice work you did with us, and we'll just wish you the best for all your new life after your PhD.
Thank you so much.
Okay, so thank you. So it's now time for the jury to deliberate. So we will stay in the room. So we will ask all the audience to wait outside, please. Yeah. And maybe you can stop the streaming.
Yeah.
Here.